Welcome. We now want to discuss Mohr's circle, and we will look, once we've discussed the theory behind Mohr's circle, we'll look at an example problem involving an airplane fuselage. Well, we already hinted to this airplane fuselage from the previous video, which we did, titled Coordinate Transformations, Direction Cosines, and the 2D Stress Wedge. So if you haven't looked at that video, you might want to first check that one out before you come to this video, because we're going to build a little bit off of what we talked about there. But as a quick recap on what we talked about there, we started with this plane stress patch as acting perhaps on the skin of an airplane. And notice that the stress patch has two normal stresses. It has so for example, I'm denoting normal stresses with the Greek letter sigma. This is the normal stress. And the Greek letter tau I'm using to stand for the shearing stress. Okay, so I've got a normal stress going in the x direction, which is sigma sub x. I have one going in the y direction, which is sigma sub y. And then notice that we have some shearing stresses that are taking place here, tau xy, and then we have tau xy going this way, and then also everything is balanced on the opposite sides. So if you have sigma x coming out this way on this face, to maintain static equilibrium you have to have sigma x going out the other way, that way. And as I've drawn this, I've drawn it adhering to the positive sign convention. So meaning that when sigma x is pointed outward, as it is here, and as is sigma y, that those stresses are tensile. It's also important to mention that this tau on this face is producing a counterclockwise rotation, and we will also take that in our sign convention to be positive. Okay, with all of that then, let us go ahead and continue. Last video we had shown how you can slice this stress patch and then you get a stress wedge. We mentioned in that video that there's an area here that I hadn't drawn in the original, this little triangle. But then we developed equations for sigma x prime as well as the tau x prime, which is sitting over here. And we were able to show the principal stresses by solving this eigenvalue problem. We had a quadratic equation that resulted from this, and we got two, of course, it's a quadratic equation, so we got two roots to that quadratic polynomial, and all of this is in that video that I mentioned, coordinate transformations, direction cosines, and the 2D stress wedge. Here is the solution for the eigenvalues. So we have a plus root, and then we have a minus root in solving for the quadratic formula. We went ahead and said that this portion is what we're calling sigma average. And then we showed that all of this is what we're calling the capital R. Okay, so sigma average is, of course, the average between sigma x and sigma y, which is here given in equation 13. R, which is all of this stuff, can be also written by bringing this 2 inside the radical, and when you do that it becomes 2 squared, So we could have a term like this, and then we can also have of course the 4 gets cancelled when the 2 comes under the radical. It becomes 2 squared, so 4 divided by 4 is a 1. That's why you don't see the 4 there anymore. And then you have tau xy squared. So we can write our eigenvalue solution, or our principal stresses, can be written much more easily in this notation, where we have sigma av plus or minus r, capital R. Okay, very good. Now, excuse me. Let me now start at this point. Now let's take the equation we had developed in the last video, the video titled Coordinate Transformations, Direction, Cosines, and the 2D Stress Wedge. We had developed that in the previous, so see previous video titled Coordinate Transformations, etc. And we developed this equation. Now what I'm going to do, I want to find where there may be any extrema. That is to say, what if there's a maximum or a minimum? And we already know the answer ahead of time because we solved the eigenvalue problem, but we're pretending that we don't know that. So using an approach by calculus, I take the first derivative of sigma x prime, as I've done here, okay, and when I set this value to 0, as I've done over here, we want to see at what value of sigma, I'm putting a subscript p, that p stands for principal. So at what angle will we have principal effects or extrema occurring? Okay, so it's a matter of solving for that theta sub p. And that's what I do here. I then divide both sides by the cosine of the 2 theta p. And when I have sine of 2 theta p divided by cosine of 2 theta p, that gives me the tangent of 2 theta p. And I also get this result on the right-hand side of that. Okay, so we have here that the tangent of the double angle is tau xy, which is the shear stress, divided by 1/2 of the difference between sigma x and sigma y. In that previous video, we had defined what we're calling R, and here it is. And now graphically, let's look at this R using Pythagorean's theorem. We know that Pythagorean's theorem says a squared plus b squared is equal to c squared. So now if you look at, I have 2 right triangles sitting here. Let's just look at one of them. I've got another one down here. But let's look at this using Pythagorean's theorem. So the square of one of the legs of the triangle, namely this squared, plus the square of the other leg of the triangle, namely that squared, has to equal the square of the hypotenuse, which this is R. Okay, the same thing happens, the same thing can be said for the triangle sitting down here. Notice that the angle in here is 2 theta p1. Okay, this angle going from here all the way around is the angle 2 theta p2. So we have 2 principal angles that we're looking for. Let's make some observations here, first of all, that when I take this equation 16a, which we developed, okay, when I take this and I divide by 2, okay, so that gets rid of this 2 over here, and that brings the 2 under this, of course. Now, when I compare this with the equation I had developed in the previous video on coordinate transformations, we had an equation tau x prime y prime. When I compare these two, I see right away that tau x prime y prime is 0. Because you notice that this is exactly equal to that, but all of this is equal to 0. So we see that tau x prime y prime is 0, and that means that, so this is an important point, therefore at principal plane, okay, at the principal planes, there is no shear stress. Okay, and as a matter of fact, that's one of the definitions of what we mean when we say principal. When we talk about the principal stresses, we're talking about planes upon which there is no shearing taking place. Okay? If we go back to the figure up above, we can say that the sine of the double angle is opposite over the hypotenuse, that is to say, tau xy over the r, or let me come back down. I could say from the two triangles that the sine of the double angle is plus or minus tau xy over the r. And likewise, from a similar argument, I can write the cosine of a double angle, just going back to that figure, is the adjacent side, which is this, over the r. And when I substitute that into this equation here, notice that I have a cosine of a double angle and a sine of a double angle. When I sub in sine of 2 theta p equal to plus or minus tau xy over r, which is this result, okay, when I sub that into this and into here, I'm going to get an equation that looks like this. And you should notice that when we come to a little cleanup, that the expression contained within this, what I've just circled here, this is what we were defining previously as our r squared. So it's r squared divided by r, and this, I hope you'll recognize that this is nothing other than sigma average. And so really we're going to get exactly what we had expected to get, namely this. Okay, that is to say, as we had noted previously, that sigma x prime is the average stress plus or minus the r value. Okay, when we make a comparison of our angle theta sub p from equation 15, we note that at this angle, that the sigma x prime, what we've been calling sigma x prime, is equal to sigma 1. It's the first principal stress. So if we were to summarize what we've said so far, we said that we have found that a pair of angles result, and that on the principal plane there is no shear that occurs, and that our principal stresses, sigma 1, comma 2, it's what we were depicting as our sigma x prime in the tilted axis, okay, at some angle. Now, taking all of this, we want to finally come in and talk about Mohr's circle. So that's the background. So in 1882, a German engineer by the name of Otto Mohr made a very interesting observation based on all of this mathematical development that we've been talking about. By setting sigma x prime to just sigma and tau x prime y prime to just tau, then we can write the following. So this is equation A.16a with, instead of saying sigma x prime, now we're saying it's sigma is equal to sigma av plus the difference between the sigma x and sigma y over 2 times cos of double angle plus tau, the shear stress xy, times sine of double angle. And if I bring the sigma average to the left, I get this equation. And also from 16b, instead of calling this tau x prime y prime, I'm now calling it just tau. I get this expression. And if I square both sides of the above pair of expressions, then I'm going to get the following. I get squaring this one gives me this result over here. And then squaring this one gives me this result. And when I add these two results together, look at how interesting this is. I get the sum of these expressions, the sum of the square of these expressions is equal to all of this. We note that this expression in the braces is just 1. Sine squared plus cosine squared is 1. Okay, and so all of this, and similarly the same it can be said for this, so all of this reduces to something like this. And so this is what Otto Mohr was looking at when he was looking at all of the math. He saw that an equation of this form results. And this equation, I hope you can appreciate that this is the equation of a circle. Okay, that's to say x squared plus y squared is equal to r squared. R is, of course, the radius. Okay, and of course we have our x squared would be, or x would be sigma minus sigma av, and then the y value would be tau. Now what Otto Mohr did is he took all of this result and he plotted this in a sigma tau coordinate axes, or a sigma tau plane. So this is what we might call the sigma tau plane, or the Mohr plane. Okay, and you'll notice that the center of the circle, which is right over here, occurs at a value of sigma average. That is to say, sigma x plus sigma y over 2 locates for you the center of the circle. Of course, the radius of the circle, which is this value, this radius is found by this expression. Okay, and we may find the angle theta p1 simply through trigonometry, because we know that this, we have these two triangles, as we mentioned before. These are two right triangles such that one leg has a value of tau xy, and the other leg of this triangle can also be found as this value. So sigma x minus sigma y over 2 is this other leg, and so 2 times, so if you were to take the tangent, for example, of 2 theta p1, it's going to be the opposite over the adjacent, that would be tau xy over sigma x minus sigma y over 2. Okay? Notice that on the principal points, which would be this one, this is one of the principal stresses. Let's call this the first principal stress. Notice that it happens on the sigma axis where tau is 0. Okay? And we expected that to happen. The second principal stress is also on the sigma axis where the so this would be the second principal stress, where the shear where there is no shearing at that point. Okay. It is also important for you to recognize that the maximum shear stress on this is just the radial distance. So I hope you can appreciate that that happens at this point, and in absolute value terms, it'll happen over here where tau would be negative. I hope you also understand that I'm drawing my tau positive going downward, and of course, as I mentioned earlier in the video, that counterclockwise is the convention for positive shearing. Okay, and all of this is being done just in accordance to sign convention. There's nothing really special about it, but we're adhering to a convention and sticking with it so that everything comes out consistently. Other people may put the tau axis going positive upward. So consistency is really important here. We note from Mohr's circle that the tau axis is drawn downward positive in order to maintain a counterclockwise positive rotation of our angles. That's what we defined from the very beginning. If you made it going up, then this would be reversed. And it is also important that for you to note that angular measurements in the Mohr plane are taken to be 2 times theta, which are in fact halved in the real scenario. Okay, so I will say a little bit more about this in just a second. This is due to the fact that the argument of equation 17, which is this one, this is the argument, is in terms of 2 theta. Okay? So, we have double angles that are occurring in the construction of our Mohr circle. After solving for this argument, the result is then halved, so you divide both sides by 2 to find the angular measure in the real world. That is in terms of the xy plane. A very simple way for you to remember what you're doing is to say Mohr, which is the name of the gentleman who conceived of this Mohr circle. Mohr is Mohr, M-O-R-E. Okay, if you just remember that simple mnemonic device, then it'll keep you straight. Now let's go ahead and do an actual problem. And here we have an airplane, and we're taking a little square patch on the skin of the airplane, and somehow we've determined the stresses acting on that square patch on the skin of the airplane to be as given here. So the normal stress in the x direction, if we call this direction x, is 5 megapascals. 90 degrees from that, it's also tensile stress of sigma y is 1 megapascal, and then we have a shear stress tau xy on this face of 4 megapascals, which is 4 megapascals going in the opposite direction on this other face. Okay, so let me go ahead and try to give an outline of a solution to this problem using Mohr's circle. So here is the square patch that we have. We have sigma x is 5 ksi. We have sigma y is 1 ksi. Actually, we were using MPa, sorry. Let me make these MPa. And then we have tau xy is 4 MPa. And of course, everything is balanced appropriately. Okay, now over here I want to tell you a little way to remember how to keep certain things straight. So let's call this the horizontal face, which is going horizontally this way, and this one we'll call the vertical face. Okay, so H is for horizontal face, and V is for vertical face. Alright, now on the vertical face we have the following coordinates. We have 5 coming outward, and then in the tau direction we have 4 that is going counterclockwise, so it's positive, and of course the units here are MPa. On the horizontal face we have 1 going outward, which is this guy, and we have a shear that's going clockwise, so it's going to be minus 4 MPa over there. So straight away we can go ahead and calculate some of the important things. For example, sigma av is what? It's the average between these two, right? So that would be sigma x plus sigma y over 2, that's 6 over 2, that's 3 MPa, and this is the center of the circle. Okay, we can also compute the r. The radial length is r, which is the square root of sigma x minus sigma y over 2, that expression squared, plus tau xy squared. Okay, so this is going to be the square root of sigma x is 5 minus sigma y is 1 over 2, that whole expression squared, plus tau xy is 4, that being squared. So this is, let me see, the 5 minus 1 is 4 divided by 2, that's 2, 2 being squared is 4 plus 16. Okay, so it looks like it's the square root of 20. That means that, which is roughly 4.47 MPa. Okay? Now, we also know right away that sigma 1, which is the first principal stress, is equal to sigma av plus r. Sigma 2, which is the second principal stress, is sigma av minus r. And so if you put these values together, you have 3 plus 4.47, and you have 3 minus 4.47. And so you get something on the order of, for the first principal stress, about 7.47 MPa. I like that because we're talking about an airplane, so 747 means something in airplane speak. And sigma 2 is equal to a minus 1.47 MPa. Of course, that just happened. That was a coincidence. And we know that tau max is just the value of r, which is this value, which is this value. Okay, so equations wise, we were able to find all of that. But now let's go ahead and put all of this stuff on the Mohr circle itself. So I'm going to draw a pair of axes here. Over here is my sigma axis, over here is my tau axis, and I'm going to take counterclockwise to be positive. And we know that we have a pair of coordinates. So V is 5, 4, and H is 1, minus 4. Let's go ahead and plot those. All right, so here we go. 5, 4, that means I'm going to go over 5, 1, 2, 3, 4, 5, and down 4, 1, 2, 3, 4. So 5, 4 is going to be the intersection of these 2 points. On the other hand, I had an H which was 1 minus 4, right? So that means 1 and then minus 4 is going to go the opposite direction. That's going to put me here. So let me label this. This is, first of all, my vertical coordinates. This is my horizontal coordinate. Okay. And now, if I connect the straight line between these two, we know that the center is going to cross at 3. So if I connect the straight line between these two, it's going to do something like this. Well, that was not a very good line. Let's try that once again. Okay, a little better. Okay. Now, of course, this amount from here to here is the radial amount, so I can draw a circle going through this. So let me go ahead and do that. I already know where I'm expecting my principal stress to happen, so let me just keep this going. 1, 2, 3, 4, 5, 6, 7, 8. It's going to be about here. So, right. And then we're going to do something like, we said that R is about 4.47, so if I were to come down straight, it should be somewhere around here. So if I were to just, and of course sigma 2 is 1.47, so here's 1, it's minus 1.5 almost. So it's going to do something like, this isn't the best circle of course, but you get the drift. Okay, that's actually a horrible circle, but if you take the time and do it by scale, you'll do far better than what I did there. So here you have your sigma 1 is 7.47. The center of the circle is at sigma av, comma 0. This is sigma 1, comma 0. And then this is sigma 2, which is minus 1.47, comma 0, is that point. And then, of course, this point here is our tau max, which is our R value, which is root 20, which is approximately 4.47 MPa. Okay, and this occurs at, of course, tau max, comma, sigma av. Okay, that's sigma av, once again, is that center point. Okay, so to kind of wrap up the discussion, let's now find the angles. So the angles that we need to find, here they are. The first angle is to take the vertical point into this principal direction. So I'm going to call this 2 theta p. Now let me explicitly write this out so you be sure not to miss this. This is the angle to take the original vertical plane V into first principal direction. Just as a reminder, let's remember what we're talking about here. We had a vertical plane, we had a horizontal plane, we had sigma x is 5, sigma y is 1, tau xy is 4, and the units here are MPa. So it's to take this vertical plane back into the first principal direction, okay, which is occurring right over here. Note also that to go from the vertical plane to where tau is maximum is going to be an angle of 2 theta s. Let me write this out explicitly. So this is the angle to take original vertical plane V into maximum shearing state. Okay? I hope that is clear for you. Now let's wrap it all up and put it all together, therefore. Okay, so I'm going to find the angles, and we can wrap it all up that way. So, finding angles. We have 2 theta p is equal to the arctangent of tau xy, this is all trigonometry, divided by sigma x minus sigma y over 2. You're going to ask me, where did that come from? Okay, so the tau xy is this leg of the triangle. And this other leg of the triangle is sigma x minus sigma y over 2. Okay? So the tangent of 2 theta p is going to be opposite, which is this one, over adjacent, which is this one. So if I solve for the argument 2 theta p, it's the arctangent of all of that. So I can find that 2 theta p is equal to about 63.43 degrees, which means that in the real world, the principal plane is occurring at 31.7 degrees, and it's going in this direction relative to the vertical plane. Okay. As for the other angle, we can do something similar. 2 theta s for the shear plane is the arctangent of sigma x minus sigma y over 2 all over tau xy. Okay? And that is equal to 2 theta s is equal to about 26.57 degrees, which means that if you have that, theta s is about 13.3 degrees going clockwise relative to the vertical plane. Alright, so to depict your answers, it is usual for you to try to draw this all out. So here's the original patch in the XY orientation. Here's the vertical face, here's the horizontal face. Once again, here is sigma x, here is sigma y. Here is tau xy, Okay. All right. Now, I'm going to draw a vertical line up. And from this vertical line, we're going to go over a counterclockwise amount by 31.7. That is to say, this is the vertical face being rotated by 31.7 degrees. So let's say 31.7 is about that amount. So that would be the 31.7 degrees, which is this amount, relative to the vertical face. On that, I have now my square patch, but my square patch is in its principal state. That means all of my stresses are maximal. So notice that all of my stresses are, I have my max and my min. So these are the extrema. I have sigma 1 is my max. My min is a compressive one. And notice that I have no shearing here. No shearing. This is principal. Okay. On the shear state, we have the following. If I come over this way, I'm expecting to come over clockwise 13.3 degrees, so it's going to be something on this order. Let me try that again. So this will be the theta S, and this was your theta P, and over here I'm going to have a patch that looks something like this. I have a state of hydrostatic pressure that's on all of these faces going out in the amount of sigma Av. Sigma Av was 3 MPa. And I have my maximal shearing that's taking place on these faces, okay? This is tau max is 4.47 MPa. Okay, having done all of that now, it's important for us to notice a few things, okay? So let's talk just a little bit more and try and summarize what we have established here. So it's important to note the physical significance of what we did. So observe that even though the planar stress state that was acting on the upper part of the aircraft's fuselage along the original XY coordinate system had the greatest magnitude of 5, the actual maximum stress value that we found was 7.47, occurring at this angle, okay, counterclockwise from the x-axis. In other words, to keep the discussion simple, if the material capacity, let's suppose it's just isotropic material, that means that at a point all of the values are going to be the same from point to point. Okay, so steel may be a pretty good macroscopically isotropic material to consider. And let's suppose that we knew that the material is going to fail at a stress of 6 MPa. It would have been completely incorrect to conclude that the design of our airplane is safe just looking at this number, because 5 MPa is less than 6 MPa, and we would be incorrect to say, oh, we're safe, because in fact, the maximum stress is far more than what is allowed for failure. As a matter of fact, it's about 50% more. So we would have been in a gross error had we made that mistake. Another observation, a final observation that's worth mentioning here is that our principal stresses were found to be of opposite sign. One was positive and one was negative. And so you may have been wondering, why do we even care about the minimal effects? Just why not look at the maximal? And the reason for that is in a situation like the one that we're looking at right now, because our minimal stress happened to be negative, meaning it's serving a compressive type of behavior. And because it's compressive, we would have to look at buckling effects of the material. So it's not enough to just say, here's the maximum stress, let's say it's tension, and we're good on that front and close up shop, because it's possible that your minimal stress is exhibiting compressive behavior, which then you need to consider buckling effects as well. And so these are some observations on what we did today. I appreciate all of your patience to study with me as we talked about all of these mathematical equations at first, and then of course the graphical, very streamlined graphical approach that we can be afforded through the Mohr circle. And I hope that you'll make use of Mohr circle and not have to memorize mathematical equations, because it's very simple. Given a stress state like this, where you have some stresses acting on that, whatever they may be, you can then very simply analyze, just going from a stress state like this, go right into Mohr's circle, and then you'll find your principal values and also the principal planes where those occur, and you'll have the maximal effects just by what would be literally a back of the envelope calculation. Again, thank you for your patience, and we look forward to seeing you in a future video.